everybody. I hope you're doing well out there, getting some sunshine before the polar vortex comes in this weekend and potentially turns everything white yet again. Um, I'm sorry for the technical difficulties I was having yesterday with this assignment. As such, and given the length of this assignment, I'm going to not do a Monday assignment, and I'll send that out in email as well. So this will be due on Wednesday. Today we're going to be talking about the periodic table. In particular, some learning objectives. One is kind of recycled from Monday. I can relate the electron configurations of the elements to the shape of the periodic table. I can determine the number of valence electrons and the ion charge of elements based off their location on the periodic table. And I can describe what a group, family, and period is on the periodic table. And the last thing I'll say is I am doing a little bit different of a format. I made this particular slide in slideshow in Smart Notebook, and as such, I've exported it as a PDF. You still have access to this PDF, but that's the reason why it looks a little different from the Google Slides. So with that, let's get right into it. Bear with me as I work the new technology. So first of all, what is the periodic table? The periodic table of the elements, as it's often referred to. The periodic table is a way of organizing the elements based upon their similarities. And you guys have looked at this plenty of times. We'll be looking at a lot of periodic tables today. But again, just a way of organizing elements. So here's an important question to start with. Do I capitalize periodic table? I say no. The reason being that there are many different periodic tables. There's not just one periodic table. The most common version is only one version, and other versions exist and look differently only because they organize the elements differently. So here you can see some very different looking periodic tables, some more circular, some more whatever that is. But one important thing to note here is if you look closely at these, you'll see some familiar letters. You'll see S, P, D, and F. S, P, D, and F. So again, really we organize elements based on their electron configurations because their electron configurations determines their chemical properties. That's what we're going to be talking about today. So the common periodic table is this one that we've seen. And we'll focus our study on the most common periodic table. We're not going to go into any of those funky ones, but I think it's fun to show them, show that they do exist when we start to study the periodic table. The periodic table is the chemist's #1 tool. So it's very important that we understand the amount of information that we can get out of the periodic table. I'm not big on the idea of memorizing the periodic table, but more knowing how to use it as a tool when you need to in the world of chemistry. So as we've said before, elements are arranged in increasing atomic number as one would read a book. That means you start in the top left and you go over to the end of the line. And then you go down a line and you read across that line. And then down a line and read across that line. So that's an important concept, one we'll come back to. And remember, of course, that atomic number means the number of protons in the nucleus of the atom. So as you read across the periodic table, in general, atoms tend to get heavier, do get heavier. So why is the periodic table shaped as it is? You read about this briefly on Monday's assignment. I'm going to do a quick recap. The general shape of the periodic table comes from electron configuration. Periodic table is divided into 4 blocks. The blocks are S, P, D, and F. And you can see them here. On the left, we have this narrow, tall S block. On the right, we have a more square P block. In the middle, we have the D block. And at the bottom, we have the F block. For your assignment, you'll have to make a copy of a Google Sheet, which is just an empty periodic table. Google Sheets works pretty well for this. Normally, I would print them out and have you color them. But here, I'm asking you to do a number of things. First off, just color the blocks to make sure that you know what I mean when I say in the p block or in the s block. The block determines the last orbital, the electron cloud shape of the element's valence electrons. This is basically telling you what letter is at the end of that electron configuration for the element. An element in the s block has valence electrons in the s orbital. An element in the p block has valence electrons in the p orbital, so on and so forth. And the rho determines the energy level. Remember, energy level is that big number out in front, and it's thought of as the distance from the nucleus. As you move to higher and higher energy levels, those electrons are now farther away from the nucleus of the atom. So the rho determines the energy level of the element's valence electrons. So you can see up here, the first row is going to end 1s. The second row ends 2s in the s block, 2p in the p block. Third row, 3s in the s block, 3p in the p block. The d block gets a little funky, and we'll cover that later, but you'll see that it's offset a row. It goes 4s, 3d, 4p. And then the f block, funkier still, is actually offset 2 rows. Again, we'll come back to that. So an element in the first row has valence electrons in the first energy level. An element in the second has valence electrons in the second energy level, so on and so forth. And then it's important to note that the common periodic table, the one we've been looking at so far, is drawn in a sort of condensed form, and we do that to save space. But the true periodic table, how it should look, is like this. And what you'll see here, if you look at this and soak in this image, is that the F block is spliced in between the S and the D block. And if you look at the atomic numbers, it does make sense. You make a jump when you go from here, it jumps down to here. We do that again just to save space horizontally so it's not super long. But do know that the F block actually belongs right here between the bottom 2 rows of the S and D block. So the shape of the periodic table is continued here. We're going to do a deeper look using electron configuration. Since the p block, since the p orbital does not exist in the first energy level, think back to the order in which you do electron configuration. It goes 1s and then 2s right away. There is no 1p possible. So because of that, the p block does not exist in the first row. And then that same pattern kind of follows still. Since the d block, or the d orbital, does not exist in the second energy level, and the 4s subshell actually fills before 3d, the d block doesn't appear until the 4th row. What I mean by this is you can look at this and deduce that order that was on your electron configuration cheat sheet. It's going to go 1s, 2s, 2p, 3s, 3p, 4s, and then the next part of the order is actually 3d, which is why that first row of the d block is offset 1 energy level from S and P. It again goes back to that order, the Aufbau principle, in which you do electron configuration. So as such, the D block is an energy level behind the row number. And then if you look at that order, you'd see that the same logic explains the placement of the F block. The F block is actually 2 rows behind the S and the P block. If you look at the filling order, that should make sense, hopefully. And then another important thing to note is that the width of each block is equal to the maximum number of electrons allowed in that orbital. So what I mean by that is S is just a spherical shape, and therefore because it only has one possible orientation, it can only hold at most 2 electrons. And that's why the S block is only 2 elements wide. The P block, on the other hand, had 3 possible orientations. If each holds 2 electrons, then that's 6 electrons that can fill in a p orbital, and therefore the p block is 6 elements wide. The d block had 5 orientations with 2 electrons apiece, is 10 possible electrons in a d orbital, and therefore the d block is 10 elements wide. Same with the f block, 14 elements wide because of the number of electrons allowed in f orbitals. So with all this said, kind of the takeaway here is that electron configuration is going to cause some weird, bizarre exceptions when things come to the D and the F block, but don't worry about that because our journey through chemistry will remain largely in the top half of the periodic table. It will be largely in the S and the P block, since those elements make up the vast majority of our world, and they're also the least complicated to understand. But it's a good rule of thumb when it comes to studying chemistry that always be prepared for there to be an exception, and then often there is an exception to the exception. So let's move into the next piece, which is valence electrons in the S and P block. So like I just said, we're going to just cut the D and the F block right out of the periodic table. We're going to make it much, much smaller. We're just focusing on the S and the P block right now. You will do the same thing in your assignment. In that Google Sheet on the second tab in the bottom left, I ask you to fill in valence electrons. And when you do that, you do not need to worry about the D block or the F block, which is why I made them light red color. So when looking at only electron configurations of the S block and the P block elements, a great pattern will quickly show itself. The number of valence electrons is equal to the column number if you just kind of ignore the D block. Remember, the D block is 10 wide. So when I ignore the D block, I think of this first column of the P block as being 3, not 13. I'm just kind of ignoring that 1 in front that comes from those 10 D electrons. So here's the pattern that presents itself. You can see that in the first column, electron configurations end S1. The number out in front, the energy level or distance from the nucleus, is determined on the row, but they always end S1. So hydrogen's 1s1, lithium's what helium was, that's what He in brackets mean, plus 2s1. Sodium is what neon was, plus 3s1. So again, they're always ending in S1, which means they always have 1 valence electron in that first column. Same's true of the second column. They always end they always end S2. Again, with the number out in front being the energy level, the row. So if they always end S2, then we can conclude that an element in the second column always has 2 valence electrons. Same's true of the 13th column, but again, remember that's really like we're thinking of it as the third column, ignoring the D block. They always end S2P1, which means when you add the exponents together, they have 3 valence electrons. I probably don't need to belabor this and go through every piece. You can see the pattern that's going to emerge here is the 13th column has 3 valence electrons, that's boron and down. Carbon and down has 4 valence electrons because of the S2P2. Nitrogen and down has 5 because of the S2P3. Oxygen and down has 6 because of the S2P4. Fluorine and down has 7 valence electrons because of the S2P5. And then finally, this last column, a very important column, has 8 valence electrons because of the S2P6. Together make 8, with of course the exception of helium, which we'll get to in just a minute. So what this all breaks down to, what I see, or one of the things I see when I look at the periodic table, is I'm instantly able to figure out how many valence electrons, or electrons on the outermost layer, exist for elements that are in the S and the P block. And I can do that just by looking at their location. So this is a nice little blank periodic table where we don't do anything with the D and the F block that shows the number of valence electrons for each of those columns. A synonym for columns on the periodic table is groups, which we will also talk about in a minute, but that's what they mean by group right there. So I said we'd talk about helium and what's it doing. So what are you doing, helium? You may have noticed, and I think I even made this a PD question in the last assignment, but you may have noticed that helium has an electron configuration of 1s2. It's got 2 electrons close to the nucleus in that first energy level and an s orbital. But helium is in the last column next to the p block, right? It's not over here in the s block forming a nice rectangular shape like you'd want and like you'd expect given that its valence electrons are in an s orbital. So helium is the removed member of the s block, placed in the last column because helium has a full valence shell. In the first energy level, you can only have 2 electrons because you only have an s orbital. So helium's 2 electrons fill that valence shell right away. Every element below helium also has a full valence shell. The second, third, fourth, fifth, or sixth energy levels in this case, which all hold 8 before starting to fill a new energy level. So everybody in that last column has a full valence shell. Helium just fills it with 2, and everybody else fills it with 8. And it's because of that that we pull helium out of the s block, where some might say helium belongs, and we put helium over in that far right column because of its chemical properties dictated by its full valence shell. So why is valence shell so important? It really is one of the most important concepts in chemistry, is those outer electrons determine how an element is going to bond into compounds and how it reacts in chemical reactions. And kind of the goal of all elements is to fill their valence shell. And so when studying quantum mechanics, when studying electron configuration, we said that 8 was the magic number of electrons to have in the valence shell. 8 valence electrons creates a full valence shell, and an element is stable when it has a full valence shell. The elements in the last column of the periodic table, helium, neon, argon, krypton, xenon, and radon, are stable because each comes with a full valence shell. We call those elements, that last column, the noble gases. And we call them noble gases because they're noble. They don't mix with other elements. They won't form compounds with anybody else. Like nobility does not mix with peasants. Every other element is on a quest of losing or gaining electrons to fill its valence shell. So I like to personify elements a lot in chemistry, and you can kind of think of filling your valence shell as being an element's goal in life. In other words, every element wants to be isoelectronic. That means having the same electron configuration with its nearest noble gas. And we see helium here has 2 electrons in the outermost shell because of those 2 in the s orbital. And then the rest of the noble gases have 8. You might wonder, well, this here on Krypton, this third energy level has far more than 8. That's because, remember, we fill 4s and 4p and then go back to 3d. So even though the 3d is filled after, it's still on the inside and not on the outside in the valence shell. So we said every element's goal is losing or gaining electrons to fill its valence shell. So that process is called ionization. Ionization is the process of forming an ion, which is an atom with a non-zero charge. And elements will lose or gain enough electrons to have a full valence shell. This means that elements in the first column, remember they have 1 valence electron, the easiest way to fill their valence shell would be to lose that one electron. Conversely, elements in the 17th column, that starts at fluorine and goes down, they have 7 valence electrons. They're 1 away. So elements in the 17th column, or the 7th column ignoring the D block, will gain 1 electron to have a full valence shell. Here's one particular love story of sodium and chlorine that kind of shows what I'm talking about here. Sodium has this electron configuration of 1s2, 2s2, 2p6, 3s1. So it's only 1 away, and if you can remove that 1 valence electron, then now your outer layer goes down, your valence shell goes down to the 2nd energy level and would naturally be full. Chlorine, on the other hand, has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p5. So it's 1 away from having a full valence shell. And so sodium will likely give up that 1 electron to be more stable. And chlorine would likely accept that 1 electron to be more stable. And by doing this trade, by sodium giving chlorine that electron, both end up with having a full valence shell. This Na plus ion, sodium ion, now has an electron configuration of 1s2, 2s2, 2p6, which is isoelectronic with its nearest noble gas. And chlorine has 1s2, 2s2, 2p6, 3s2, 3p6. So both of them, long story short, get to 8. Sodium gets there by losing 1, chlorine gets there by gaining 1. Atoms will lose or gain the most convenient amount of electrons to get to that full valence shell. So when you go through ionization, when you lose or gain electrons, you form an ion. And if everybody's doing it to try to get to their nearest noble gas, what that means is certain elements, depending on their location in the periodic table, will have to lose or gain a certain amount of electrons. So certain elements take on only certain charges to perfectly fill their valence shell. Like we just talked about with sodium, it's got 11 electrons. If it loses 1, it's got the same electron configuration as neon. Same's true with, say, potassium. If it loses 1, it's got the same electron configuration as argon, basically going 1 step back in the periodic table. Firstly, calcium, for example, has 2 valence electrons, so its nearest noble gas would also be argon if it could only lose both of those electrons. And so the pattern that forms out of this is the whole first column will take on an ion charge of +1. The whole second column will take on an ion charge of +2. And then now we're, again, skipping the D block because that's funky. We get over here to the column that starts with boron. It's got 3 valence electrons. It could either lose 3 or gain 5. If it gains 5, it gets to neon. If it loses 3, it gets to helium. And it's easier to lose 3 than it is to gain 5, simply because 3 is a smaller number. And so boron and the elements below it will gain an ion charge of +3. Carbon's in the middle. It could either gain 4 to get to neon or lose 4 to get to helium. So carbon and those elements down kind of have a choice to make about which way they want to go. The ions could either be a +4 charge or a -4 charge. Either way would get them to be the same, to have the same number of electrons and therefore electron configuration as their nearest noble gas. And now we start to go into the negatives, because nitrogen has 5 valence electrons, and so it could gain 3 to get to 8 valence electrons and be like neon, or it could lose 5 to get to be like helium and have the same number of valence electrons. For nitrogen, it's easier to gain 3 than it is to lose 5, simply because 3 is the smaller number. And so nitrogen, gaining 3 negative charges, gaining 3 negative electrons, is going to take on a charge of -3. And that's true for every element below nitrogen as well. Oxygen's got 6, so it could either gain 2 or it could lose all 6. It's easier to gain those 2 than it is to lose the 6, so oxygen in that column below it are going to take on an ion charge of -2. And then lastly, fluorine, chlorine, bromine, and iodine, they all have 7 valence electrons, so they're only 1 away. They only need to gain 1 negative charge to get to 8, and that's far easier than it is to lose all 7 to go back to the nearest noble gas. So when it comes to predicting the charges of ions based off of the electron configuration and that idea that elements want to get to be like their nearest noble gas, these numbers are extremely important to remember, which is why I ask you to plug these numbers into a periodic table as well by selecting the third tab in the bottom left. Then elements, once they have their charges, once they've formed ions, are going to come together to form neutral ionic compounds. We'll get to that in a later lesson, but the idea there is sodium with a +1 charge can bond easily with chlorine with a -1 charge because +1 and -1 will cancel each other out. All right, so I know this is a lot of information, but we're almost there. The next important distinction for chemists to make when looking at the periodic table is a metal versus a non-metal. And you might define a metal as something that's shiny or hard, not easily bent or broken. But to a chemist, a metal is defined as an element that is likely to lose electrons when it ionizes. And if you're losing negative charge, that means you're going to become positive. A nonmetal, on the other hand, is an element that is likely to gain electrons upon ionizing. Gaining electrons, gaining more negative, means my net charge would become negative. And then, of course, we have kind of an exception here. A metalloid is in between. That's where it can lose or gain electrons upon ionization. And so when we look at the periodic table, you might have noticed before that there is a staircase along the right side right here. And the staircase is what separates metals from nonmetals. Metals live on the left, nonmetals on the right. And you can see there's way more metals than there are nonmetals. So remember that the staircase divides metals and nonmetals, and metalloids fall along that staircase. The shape of the staircase occurs because of this bizarre exception with the D block and F block. You might think, well, shouldn't carbon and down be the metalloids because they can lose or gain 4? Again, weird things happen with the D and the F block, and that causes the staircase to be a staircase and not just a wall. All right, that brings us to our next piece about the periodic table, which are our groups. A group is a column on the periodic table. Very specific definition there, a column. Groups or columns have the same number of valence electrons and therefore share similar chemical properties. And your common groups are the alkali metals, which is the first column, the alkaline earth metals, which is the second. You hear a lot about those two columns in the S block, alkali metals and alkaline earth. And then other important groups that I would point out are the halogens, which is the 17th column, or the 7th without the D block. That's fluorine, chlorine, bromine, iodine. And the noble gases, which of course is the last column, which we talked about. Elements in those columns have similar properties because they all have similar amounts of, or they all have the same amount of valence electrons. So if everybody's already got their full octet, then that means they don't need to react to fill their valence shell, and therefore they're all non-reactive. Or if everybody in the first column only needs to lose 1 valence electron to fill its valence shell, then that can be very easily done, and the first column would be very reactive. I kind of just said this, but for example, the noble gases are non-reactive because they already have a full valence shell. The halogens are very reactive because they only need to gain one electron to complete their valence shell. And the alkali metals are also very reactive because they only need to lose one electron to complete their valence shell. It's a good rule of thumb that the middle of the periodic table is the least reactive, and as you get out to the edges, you get more and more reactive, with of course the exception of the last column being non-reactive altogether. So let's talk briefly about the D block and something that we call families. A family is a collection of elements that have similar properties despite not being in the same column. It's a looser definition. A famous family is the whole D block, which we call the transition metals. The partially full d orbitals of the transition metals in the D block causes these metals to be able to take on a variety of charges, not a single one after ionization. And how you should think about that is the transition metals have charges that can transition, and that's because their electrons can transition between s, d, and p orbitals more easily. So again, the whole D block we call the transition metals. You'll hear that a lot in chemistry, so it's a good word to know. And then within a family, like the transition metals, you can still have groups. An example of this would be the coinage metals. So right here in this column, we see copper, silver, and gold. Those are the coinage metals because we make coins out of them. Other families include the lanthanides and the actinides, which are the F block. Note there, though, they're grouped by row and not by column. Which brings us to periods and periodic trends. Another name for row in the periodic table is a period. This is because certain properties vary as one moves across the row of the periodic table. And then when one returns to that original column, say the first column, the trend, the period, resets itself. So period is something that happens every so often. And so here we see trends that are happening with every row. And that is where the periodic table, of course, gets its name from. So a periodic trend is a property of the elements that increases or decreases as one moves across a row, period. And here are some periodic trends, and we will run through these quickly. Atomic radius. If we think of atoms like a sphere, if we simplify them down to a sphere, the atomic radius is the distance from the center to the outside. So it's kind of a measure of how large the atom is. The atomic radius or radius of an atom increases as one moves down into the right of the periodic table. So what I mean by that is we talk about periodic trends by saying in what direction on the periodic table is that property maximized. So you can see that looking at this, where we visually display the size of atoms, cesium down here is the largest, which means that atoms down and to the right have the largest atomic radius. But if I were to look at this, like we were just describing, as I move across a single period, say the second row, you can see that the atomic radii are getting smaller. And then I go down to the next period and the trend resets itself. It starts large and then it gets smaller. And then I go down to the next row and it starts large and then it gets smaller. So that trend is happening periodically. And then when we look across periods, we can see that as you move from row 2 to row 3 to row 4, within the same column, they are getting larger. And so that tells us that down is larger, and then looking across a row tells us to the left is larger. Next is the ionization energy, or the energy required to remove an electron from an atom. And that increases as one moves up into the right on the periodic table. So in other words, up into the right is going to be the hardest to remove electrons from atoms, which makes sense about what we just talked about. Nonmetals, elements that want to gain electrons are going to hold on to the ones they have more tightly. So that's another periodic trend to be aware of. Ionization energy increases up into the right. And then lastly, probably the most important of the periodic trends is the electronegativity. The electronegativity is the ability to attract electrons, the ability of an atom to attract electrons. And an atom increases its electronegativity as one moves up and to the right on the periodic table. Closely related to ionization energy in that if it takes a lot of energy to remove the electrons I have, then that means I'm also going to want to attract in more easily. And so that was a lot of information. A lot of it is kind of just these are things that you should look at when you see the periodic table, or things you should think of when you look at the periodic table. Do your best kind of breaking down that assignment. You have a whole week until next Wednesday. Shoot me questions, concerns as you have them, and I will see you all on Tuesday for our quick little 15-minute check-in. Other than that, have a great weekend, and I'll see you when I see you. Bye, guys.